So welcome everybody. This is the July OpenXLA monthly community meeting. Thank you so much for joining us today. We've got two topics, so this meeting will be broken out into really two parts. In the first half, we've got Intel presenting with Google on the great work that they've been doing around CPU quantization support in XLA. And then the second half of the meeting, we're going to talk about all the great work that the Google DeepMind team has been doing in partnership with Google's Core ML team around Shardy, which was formerly known as Chardonnay during OpenXLA Dev Lab. So very exciting. So definitely going to be an amazing meeting. So with that, I'm going to turn it over to our to Sandeep and to Mahmood from Google's Core ML team, as well as Intel, to talk about quantization support for CPU and XLA.
Thank you. Yeah.
Take it away.
Go ahead. Yeah. Please.
Yeah. Okay. Yeah. Thank you. Hello, everyone. This is Mahmoud from Intel. So, yeah, we will be talking today about the new RFC for adding support for quantization in XLA. Sandeep and I will go over that. So, starting with the agenda here, we will start with giving a quick background about the current situation of quantization. This is the non-XLA path, what we currently have, and why we need a new solution for quantization for supporting quantization in XLA. And then we'll talk about the proposal, the RFC itself. We'll talk about how we will generate a quantized model using the Intel quantization tool, and then how we will lower that model into XLA HLO level, from TensorFlow to HLO level. And then we'll talk about how that will be compiled and executed using 1DNN library. And then we'll share some results that we have obtained through the prototype we have done. And finally, we'll talk about some conclusion and future works, and we'll open it up for Q&A at the end. And please, during the presentation, if you have any question, please ask. So the background here, we have been supporting quantization in TensorFlow, the non-XLA path, for a while, and for that we rely on the Intel tool that is called Intel Neural Compressor Inc., which provides a mechanism to generate optimized and quantized models that will deliver significant improvements in performance of hardware. So right now, the way it works, so Inc. generates a quantized model, quantized TensorFlow model with this, like with the following characteristics. So basically, it runs the calibration on the model itself, and then it relies also on legacy quantized and dequantized TensorFlow ops. So TensorFlow has some legacy ops for quantize and dequantize that are not aligned actually with the newer form for that Stability Law has of these, the definition and the signature of these ops. They're not aligned. And also Inc. Currently with a non-XLA path, it generates a model that has in it, it does all the fusions beforehand on the Inc. side, before even we start the execution with TensorFlow. So, for example, the generated model would have a node that is called a fused quantized quantity or fused MATMAP, and that is only defined defined in TensorFlow core level. And basically, this is not in any way part of XLA flow. So with all of these assumptions, there is no way to take whatever Inc. generates today and lower it and execute it with XLA. So that's why we needed a new way to generate a quantized model that can easily lower to XLA and execute it. And also, we need to align more with the stability law of definition since stable HLO has the new definition for uniform quantize and dequantize. So we need ops that aligns with that signature and also the expected functionality of these ops. And finally, we need a form that can be easily, with minimal changes, go through the TF to XLA bridge that's currently there and supported in TensorFlow. So probably many of you are already familiar with the QDQ form. Just giving a quick overview here about this form. So this is just a simple form that takes an original OP32 model, and it looks at certain ops that we care about, which are the compute heavy ops, contraction kernels like matmul and convolution, and it just inserts before each of these a couple of ops which are uniform quantize followed by a uniform dequantize. So it's like just some kind of fake quantization. And the reason we do that is this allows us to do the calibration in the model, so we can verify the accuracy. And also it allows us to keep the model as simple as possible. So it's only require 2 additional ops to the original models, and it does not deal with any fusion. At this point, like compared to what we have before, this QDQ form will not have any fusion at this point happening. And also the ink tool supports the per channel quantization schemes for the weights, where the per channel is the default one and usually gives the best accuracy results. Next slide, please. Yeah, I think the next set will be talking about how we lower quantized TensorFlow into HLO, and I think Sandy will talk more about this.
Thank you, Mahmood, for that insightful overview. I'm Sandeep. I will be taking from here, present how the quantized HLO is lowered to stable HLO. This slide in particular illustrates the current process of lowering quantized TensorFlow models to HLO. We start with a floating-point TensorFlow model in QDQ format, as Mahmood already illustrated, which is quantized using the interneural compressor in post-training quantization mode. The MLR-based TF to XLA bridge then converts this quantized model into a stable HLO model in QDQ format, where the quantize and dequantize operations are explicitly represented. And finally, we can see a stable HLO code snippet demonstrating the QDQ format. For example, the convolution takes 2 operands, which are quantized and dequantized respectively, before feeding into the input. Next slide, please. This slide highlights a hurdle in directly translating quantized stable HLO model to HLO for execution. This is mainly because stable HLO supports quantized types and operations, whereas HLO, which is XLA's compiler IR, does not. The question mark here actually emphasizes this gap. Next slide, please. This slide delves into the solution for bridging the quantization gap between stable HLO and HLO. Thankfully, stable HLO optimizer pass already provides a particular pass which converts quantization and dequantization operations into equivalent integer math operations. We'll leverage that pass here. The code snippet demonstrates how stable HLO quantize and dequantize operations are transformed into a sequence of integer math operations. For example, the stable HLO quantize operation at the top, it implements, actually, it semantically equivalents this formula about clamping and rounding to min and max. Same for dequantize operation. The stable HLO operation that you can see at the at the bottom region is actually implementing this formula in integer mathematics operations. Next slide, please. So this slide represents the overall workflow after incorporating this optimizer pass. The quantized TensorFlow model is first converted to stable HLO model with explicit quantized dequantized operation. The optimizer then transforms that into a stable HLO model with integer computations. Finally, the XLA translate tool kicks in, which converts this stable HLO model into an HLO model, which also contains integer math operations. It's worth mentioning here that we have plans to investigate the use of HLO composites, which is similar to stable HLO composite operations, to simplify the pattern matching of the decomposed HLO. And with that, I would like to hand it back to Mahmood, who will delve deeper into the compilation and execution of HLO for XLA CPU backend. All yours, Mahmood.
Yeah, thanks. So yeah, at this point, as Sandeep mentioned, we are already in the HLO level. We have converted or lowered the model to be in HLO level. So currently, what we have in 1D, we have 1D entry writer that already supports several fusions for all the precisions like FP32, BF16, and so forth. So we already have support for those kinds. So the idea here, so these fusions, we just rewrite them into custom calls, and then we call the 1DN library for execution of these custom calls. So the idea, the new thing that we are proposing here is that we need to fuse additional patterns, which are the uniform quantized pattern and the uniformly quantized subgraphs. So those patterns we need to are additional things that we need to fuse. But the idea is to leverage whatever we have for remaining fusions, so we don't have any duplication. Also, we are just the note here that we are targeting a mixed precision support of int8. That means we don't expect everything to be running in int8. Rather, we have some cases where we don't have support for int8. In these cases, we will fall back to the FP32 and F16 precisions. Next slide, please. So this just shows us how we will do the pattern matching. So the 1D rewriter will see this form, the first one in yellow. It's again a QDQ pairs before every contraction kernel, before every convolution and matmul. So we will have two visits or two passes. So the first visit will look for all the dequantized ops and will fuse them into the following contraction kernel. In this case, we have dequantized and convolution. We have two cases. Both will be fused into custom calls. And at the same time, this pass also will look for all other possible fusions that we currently support, even for other precisions. In this case, we have the bias and ReLU are supported if fusion. So we will be fusing at this pass dequantized convolution, bias, and ReLU into custom call. And after we are done with all possible fusions, a final pass will be needed just to check if there is a possibility or if there is a possibility of frequentization fusion, and that is happening where we have two custom calls with only a quantized node in between. This quantized node will be eliminated to achieve the best performance. Usually, keeping the flow in int8 as much as possible is the best for the speed up. So here we have the prototyping results. We have done a prototype and we have validated the work or the prototype with two models. We ran ResNet 50 and BERT large on squad dataset. So as we see here, the most concerning part of quantization usually is the accuracy. So we have achieved good accuracy compared to the baseline. We have very minimal loss and ResNet 50. Less than 1%, as well as in BERT large as well. And we have seen that several fusions are happening for convolutions such as bias ReLU, and for BERT we have GELU and linear and bias. Okay, so finally, so we have already published this RFC, and we do appreciate any feedback from the community on that RFC. I think it's going to be open maybe for a couple of weeks. Maybe Sandeep can confirm later. And then the future work that we are planning to do is we need to quantize more models with the prototype and to validate more models for accuracy and performance. And also we need to add more work to allow the fallback to be F16. Also to achieve the best speed up. Right now the fallback is happening to P32 whenever we don't have support for int8. And finally, we need to add also some improvements as well to the performance by trying to supporting the data movement ops. That means those data like transpose and reshape it cast, these kind of ops that usually don't affect the underlying tensor or underlying buffer in terms of scaling. So these should be easy to support and accommodate for these in the pattern matching. And finally, we will be, of course, submitting the PRs for the work we have done for the 1DN rewriter changes. I think that's all what we have. We can open it now for Q&A.
Perfect. Great. Thank you so much. So we have a few minutes reserved for Q&A. Are there any questions?
So these quantize and dequantize ops, how generalizable is it to other data types? Currently, you support int8, FP16, and BF16. Am I right?
Yes, I think it's only supporting. So there is support for int8 as well as int32, but this RFC, our proposal, is trying to avoid the int32, although it is supported by the op definition. But to simplify things, I think we don't need to go into int32. We can only live with the int8 and real type, which is either float or BF16, float 32 or BF16.
Okay, thanks.
Any other questions? Yes, Reed.
So on the TensorFlow side, is ink only for CPUs? Because the general concept could apply to any device of introducing these quantize and dequantize ops on the TensorFlow model.
Yeah, on ink side, I think no, it's not. Although this like marked maybe for CPU the RFC, but the generated QDQ form can also be lowered and executed by GPU. I don't think it's a device specific thing.
On the TensorFlow side, though, is like the ink tool will only introduce, like it only runs on CPUs, right? Or does it also run on any arbitrary device?
So we are targeting. Yeah.
Go ahead, Mahmoud.
Yeah, we are targeting CPU, but as I mentioned, if there is ink, I don't think it's adding any assumption for the device. So it's generic. So we can also use ink to generate the same model to run on GPU.
Yeah, it makes sense.
Yeah, to clarify more, so ink emits generate TensorFlow op that later on in TensorFlow, if 1DNN is enabled for CPU, it will convert that TensorFlow quantize dequantize ops into 1DNN custom ops and run. So if other backends want to support that same ops, they can also support that main TensorFlow ops. Yeah, but for 1DNN, for TensorFlow, it will convert those ops into 1DNN custom ops and run on CPU.
Yeah, I imagine the current form, the fusions are very CPU specific. But to the stable HLO path, the stable HLO seems to look a lot more generic.
Yeah, since we are talking about this, maybe we should also look into how we can reuse the pattern matching passes from GPU for quantization as well. Because they have similar logics, right?
Yeah, I'm not very familiar with the current pattern matching passes on CPU, but conceptually, I would imagine the pattern matching on GPU versus CPU on the XLA side are very similar. But perhaps the set of ops you actually could pattern match are slightly different.
Got it. Thank you.
Like, are the PRs, I assume they're gonna, like, are they gonna try to reuse logic from the GPU passes or instead just re-implement it and integrate into the existing CPU passes?
Right now in the RFC, oh, sorry, please go ahead,
Mohammed. Sorry. Yeah, right now we are just implementing it for because as I mentioned, we already have fusions for CPU and we would like to to use the same existing pattern matching for other fusions. That's why it's kind of only a CPU. Although the pattern for quantize and dequantize can be generic, but we have all the CPU fusion in a certain place where we need to leverage all of these without with minimal changes, basically.
Yeah, that makes sense. I think the best long-term design would be have a unified like pattern matching system for CPU and GPU. But in the short term and perhaps even the long term for pragmatic uses, it might be best to keep them separate if it's more convenient for you.
Yes, I think there was a discussion earlier. Maybe it's not even quantization related, whether we need to merge all of these pattern matching for both devices.
On the GPU side, we actually might eventually get rid of some of the pattern matching. So the future there is unclear, but it currently exists. And I do think it would be useful if you could merge it with the CPU pattern matching. But I think like since you already have all the infrastructure for CPU and that would be a large effort, it should not be a blocker for any quantization work you want to do.
Makes sense.
Perfect. Great. Thank you, everybody. Any other questions? I know we need to move on, but please, we can definitely continue this conversation offline. So fantastic job. Thank you, everybody. All right, let's move on to Shardy updates. Bart and Juan.
Hey. Yeah, so since I was going to give a bit of an update on Shardy. So to quickly recap, Shardy has been like a joint project between the GSPMD and PartyArt teams within Alphabet. To create a new partitioner using kind of like the learnings we both had from like, I guess these last few years, partitioning research models and some production models. And like we want to take the both approaches, like the best lessons learned and the best features from both systems into a new partitioner that we're calling Shardy. The goal is we want to kind of replace the GSPMD propagation system and the partitioner within XLA long term. Some of the like kind of highlights are like we want to be dialect agnostic, so you can use stable HLO, MHLO, or whatever dialect you want in MLAR. We're using named axes, so the shardings are based on like data axis and your model axis. And we also want to spend a lot more time improving how users debug their models, like improve the tooling and improve the kind of feedback loop about like what happens when you get an out of memory error, and if that's the result of partitioning, how can you find that out? For any more info, can you look back at the March 26th OpenXLA meeting? Also, FYI, it was called Chardonnay back then, but the official release name is now Shardy. I think a few weeks ago, we've open sourced Shardy, so now it's available on GitHub. We're not accepting PRs just yet, as we kind of open sourced it early on, but we still need to set up a bunch of like the continuous integration and some pull request infrastructure. So that's still in progress. Similar in the repo, you'll see like, similar in the repo, you'll see some Python bindings. Those don't work. There's like a unit test in there that doesn't work, but that will be fixed eventually. Initially, they will be working through JAX. Next slide.
Thanks, Bart. Currently, we have been working on to replacing integrate Shardy into the XLA pipeline, such that we can replace the Shardy. We can replace the original XLA SPMD partitioner with the Shardy system. Such our target is that users can have a smooth transition from the previous XLA pipeline into the new Shardy pipeline. We have been open source the Shardy. We have open source integration of the Shardy into the XLA in the pipeline, and we are currently working on to mitigate the performance gap between the XLA GSPMD partitioning system and the new partitioning system. And we are just working on the internal benchmarks for the TPU, but we are planning to support the GPU and CPU by the end of this year, and trying to have the users have a smooth translation. Further, currently since the XLA pipeline, XLA GSPMD are in the intermediate stages of the whole pipeline, such that the Shardy are also in the intermediate stage. We are trying to move the Shardy into the first stage of the whole pipeline, such that we can just reduce the compilation time and ease the user and simplify the whole process to help users to observe the behavior of this new partitioning system. Next slide.
So also, I guess we also want Shardy to both be integrated within JAX and PyTorch, so that when you lower your program to, like, say, stable HLO, you also see your Shardy shardings and your Shardy ops. So first, we're starting off with the JAX integration, and just I guess we have some PRs kind of out for review, and hopefully by the end of the month, most will be mostly complete. There might be some little small edges that still need to be finished, but for basic program with sharding constraints or input and output shardings, we want to be able to get it working by the end of the month. Next slide. Zishwan?
Yeah, in the Shardy, there is an update on this Shardy propagation algorithm. We just built a pipeline, including a full hierarchy, which we'll be demonstrating in the next slide. This one is just an interface for the users. Users can just register and add the propagation pipeline for their own use. And the input for this pipeline is original program without sharding propagated along the whole program. With users can specify specific sharding annotations for specific operations and several specific ops we provided in the Shardy. And we will generate a module with sharding propagated along this whole module and trying to do some optimization, especially for for example, for the constant splitter, for the DCE, and for we also inline specific functions to help the process of the sharding propagation. Next slide. Yeah, here is one of the full hierarchy of the sharding propagation under the interface of this pipeline. We have 4 levels in this hierarchy. The first one is the user priority propagation, which is the outer interface. Users can specify their own priority for specific operations. For example, users may prefer the batch dimension over other dimensions, or just, for example, they can specify they can propagate shardings along the batch dimensions first, and then do the zero optimization. And second one is the operation priority propagation. This one is borrowed from the existing XLA sharding propagation. We just try to propagate shardings for the specific operations at first, and then propagate shardings which maybe which may introduce more conflicts. For example, we will just propagate the element-wise operations at first, and then do the matrix multiplication propagation. And third one is the aggressive propagation, which is how we handle the conflict in a single priority. We'll just demonstrate more examples in the next slide. The bottom level is the basic propagation. We just try to do the propagation along a single priority and with a specific strategy. Yeah, next slide. Yeah, this slide just demonstrates how we resolved conflicts and what the conflicts are in this sharding propagation. The conflicts are just incompatible propagation choices in this process. I just using a simple element-wise operation, the add as an example. We have this one is just says the A plus B, and the simple method is trying to propagate axis along a single dimensions to all tensors. For example, if there is no conflict, we can propagate the x along dimension 0 from A to other tensors to B and C. However, I just demonstrate 2 types of conflicts in this table. The first one is the conflicts across dimension. We have known that the axis x appears in 2 dimensions at the same time, and we cannot decide which dimension of the C will have this, which we can have this propagated axis, and that's the first conflict. And the second one is that we may have the conflicts within the dimension. For example, for the dimension 2, the tensor A has the axis y and tensor C has the axis z. We cannot determine which axis will be propagated to the tensor B. These conflicts are directly corresponds to the collective operations, and these conflicts were just converted to the specific the reshard the collective operations in the partitioner directly. And how we resolve conflicts directly demonstrates how we the trade-off between these collective operations and have impact on the final result directly, such as the peak memory, the number of collective operations, as well as the execution time. And we are working on this. We are working in progress to resolve these conflicts, and we have several specific strategies to avoid the redundant collective operations. Yeah, we will have a detailed documentation and presentation in several months. The next slide.
So far we have some like really basic debugging, like ways to kind of debug Shardy. I think so. Firstly, I think XLA already has this existing XLA dump2 flag. When you specify it, we're going to put a bunch of these like intermediate file dumps inside that same directory, but like the Shardy subdirectory. Stuff like where it's integrated inside the XLA pipeline, like before import, like after import, after every user priority propagation step, then a final step, and then like after export, when we give it back to XLA with the MHLO shardings. We also have like this SDY opt tool, which those familiar with like MLAR, there's like an MLAR opt tool. Essentially, it's the same thing, but with a bunch of extra passes and pipelines registered to it that we've defined. And some future work to kind of, just kind of, let you know what we're kind of thinking about is, what we're initially thinking is, when people are debugging their models, they sometimes don't know where an axis comes from. So thinking, you're in the middle of a program, some random intermediate value, you see it's started on axis data, but you're wondering, why is it sharded on axis data? Like, what caused it to be sharded on the data axis? Like, it's always because of some users like input or output sharding, or some like constraint in the middle on some intermediate. And we only kind of provide some information exactly like how it became sharded on the data axis, like follow the path back up to the source. But that's, yeah, a little bit of a long-term vision. Maybe we'll talk about in a few months. Next slide. We also have this thing called the SDY shell. We will open source kind of eventually as well. It's essentially a CLI tool for running Shardy, but with also a bunch of like XLA integration specific utilities. There's some of these commands about specifics to XLA integration, where you want to convert between different like IRs. Like if you want to jump between HLO and like stable HLO, you have the 2HLO and then 2MLAR, and a bunch of just different commands to run different pipelines. Also, like we have commands for like running how to partition your program, so you can shard some value, like %arg0, for example, replicate it, so you can add meshes, add axes. And then run some different passes, like you can propagate, and you can also partition. And then a bunch of these debugging stuff, like you can print your program, print a smaller contexts, print number of collectives, etc. Next slide. Oh yeah. One thing I guess as well is I forget if I mentioned. I think maybe when Zishwan earlier was talking about how it's in the pipeline. But just to double check, when we have Shardy integrated with GSPMD right now we're only focusing on a propagation system this year, and maybe next year we will start working on the partitioner. So far with the way Shardy is integrated, we still rely on GSPMD partitioning, so the system that introduces the collectives. Shardy at the moment just does the propagation, so pushing around the sharding attributes, which I'll actually show you right now. So this, I'm showing a little bit of demo. On the top left is just this little JAX program. Essentially, there's a contract dimension map mol with a bunch of element-wise ops. And this is the stable HLO on the bottom right. So let me share my screen quickly. Window, export shell. So here we have the shell. And if we print, here we have the whole program, and when we type help, we have a bunch of these different commands of what we can do with this program. And I guess the first thing is, this is just a vanilla program with nothing that's Shardy specific. It's just pure vanilla stable HLO with some extra, like some string attributes that JAX adds. So let us add a mesh. So we go add mesh, and let's call it mesh. And let's add an axis to it. So we go append axis on named mesh. Let's call it the model axis, and size 8. And now when we print it, we now see that we have added our mesh. And now let us actually shard some tensor. So looking up here, the command is shard. And let's go %arg0. And just to show like the contract dimension map mole, the contract dimension on the left-hand side is dimension 1. And then we do shard on axis mesh and the model. Now we see it has the sharding. And before I go one step further in action propagation, to kind of show you exactly what we mean by kind of being dialect agnostic, the way kind of we want propagation to be dialect agnostic is through these sharding rules, which I think maybe we talked about in the previous OpenXLA community meeting. If not, it might be in some RFC somewhere. We have these sharding rules, and essentially stable HLO tells Shardy all these different rules of how to partition the tensor. And it's through these kind of rules. So if we look at the add here, for example, it's essentially saying like, oh, if dimension 0 of the left-hand side is sharded, also the dimension 0 of the right-hand side and the output dimension 0 should be sharded. Just like a little FYI, but let me undo that. And now we're back to the same module with the sharding, and we run propagate. And now we see that it has propagated %arg0 down to the adds, where it has the sharding here. And then %1 gets fed into the dot general. And because contract dimension map mole, the output needs to be all reduced. So there's no sharding to propagate any further. It needs to be fully replicated. If we fall back to %3, this has been partitioned. And fall back to arg1, this has also been partitioned. And then, for example, because how XLA wants to still, because how GSBMD partitioning still relies on MHLO shardings, we can still dump the equivalent MHLO shardings with those string attributes of op sharding v2s. So yeah, I think that's kind of the demo, but I think we'll eventually open source this and make it available for people to use and debug stuff. We found it pretty helpful personally. I think that's all. And I think that's all I have to show for Shardy today.
Awesome. Let's open up the floor for questions. Kevin?
Yeah, just curious why you went the shell approach as opposed to like command line that takes in several flags.
So I guess you have the SDY opt tool already. So that's kind of the equivalent, I'd say. I guess what we kind of found helpful is sometimes you realize like actually, oh, you did the wrong thing. So we also like an undo command. So we can very much quickly like undo it and revert. Be like, what if you partition this one and propagate? Oh, let's see what happens. Oh, okay, let's undo this one step. So it makes it a bit more kind of easily iterable and like easy to do it at once versus changing this like a big command line flag.
Can you dump your session as a Shardy opt command?
No, because I guess when it comes to like some of those commands, like shard some tensor, that's not like let's say a pass, not like an MLR pass. It's like go into them and manipulate that argument.
Yeah, but you can dump two files. Like one of the things that the shell can do, which we found quite useful in debugging.
Yeah, but I guess we can't use the opt tool afterwards.
Yeah. You can also run HLO passes, like partitioning and then dumping and then moving to and from MLR and HLO.
Any other questions? All right, fantastic job. All right, I know we're going to wrap up here. Just a quick reminder about OpenXLA documentation. We do want to try to make it better. We've heard some feedback about onboarding, and as we're trying to collect everything. So if you can send that over by end of week, there's a survey that I emailed out in the emails. If you can just fill that out by Friday, that would be awesome. So we can help to make the documentation for OpenXLA much easier and better for everybody. That's all I've got. I know we have 3 more minutes left, so I can just open up the floor to see if anybody's got any comments, questions, concerns that they want to bring up. All right. If not, fantastic job. Thank you, everybody.